give a brief introduction to this webinar, to the webinar series, and also to help a little bit moderating questions and answers from you, the audience, to our speakers today. So just to kick it off, this is the third webinar in a three-webinar series this year. As you can see by my title slide, this webinar is looking at aquatic interactions with MHK devices, and it's really the second part of a two-part series looking at aquatic interactions. Our last webinar in August looked specifically at some of the research coming out on the effects of aquatic interactions. This webinar is looking more closely at how we actually conduct that monitoring. So what are some of the technologies and strategies for doing that kind of monitoring activity? So next slide, please, Anna. So the MHK Environmental Webinar Series came out of discussions with the Federal Renewable Ocean Energy Working Group, which is a working group that consists of pretty much all of the federal agencies involved in regulating or planning for marine and hydrokinetic energy and also offshore wind. This working group realized the need to do a better job of disseminating the results of information coming out of studies being funded by federal agencies and also studies being funded by device developers. So they formed a subgroup consisting of NOAA, DOE, MRE, DOE, and EPA to look into methods for information dissemination. And the webinar series came out of that, came out of those discussions. I work for Pacific Northwest National Laboratory, and the role of my lab is to help provide technical assistance and do some of the facilitation for the webinars, as well as we also host the completed webinars. This is being taped, as were the other ones, on our environmental research database known as TETHIS, and I'll give you a link to that in a second. The goals of the webinar series are threefold. First, to identify gaps and priority areas for future research efforts. Second, to communicate ongoing studies and results. And third, to help inform siting and permitting efforts. Next slide, please, Anna. So as I mentioned, this is the third in a three-webinar series for fiscal year 2011. The first webinar was on data management, risk assessment, and cumulative effects analysis. That was on July 27th. And then as I mentioned, on August 29th, we had a second webinar on aquatic animals and device interactions. Both of these webinars are housed at Pacific Northwest National Lab's TETHIS website, and you can see the link at the bottom of the screen there. So if you'd like to, this webinar will be housed there as well. If you'd like to see the presentations or watch the webinar in its entirety at a later date, you can do that. Next slide, please. So today's topic is focusing on developing methodologies for monitoring MHK devices post-deployment, including monitoring framework development, and with particular focus on the use of passive and active acoustic technologies to monitor aquatic animal behavior around MHK devices. The webinar will also highlight how monitoring techniques and technologies can be used to develop mitigation measures in the future as needed. As I mentioned, this is a continuation of the August 29th webinar, which focused on animal-device interactions, and where that webinar was really about the what, this one is more about the how. As you all know, this is an important topic area. It's an important topic area for regulators and for device developers working through some of the complex environmental problems with siting and permitting these devices. And our intention of this webinar is to communicate information that could help with that process. And I think that the subject matter of this webinar really reflects a fact that we're moving into an MHK development phase where pre- and post-deployment monitoring is a major research focus. And understanding how that monitoring can be used to inform mitigation and adaptive management in the first generation of MHK projects is certainly a focus of the water power team. So on this slide, you can see the speakers that we have slated today. I think rather than read through this slide now, I will introduce each as their talk comes up. But we have an excellent panel today. I think we have 7 talks, all experts in the field. And what we're going to do, and if you want to go to the next slide, Anna, is each speaker will be given a 15-minute period for their presentation, followed by a 5-minute question and answer. I will give the speaker a 5-minute warning so they'll hear me chime in. As far as how to actually do the question and answer period, if you all see on your control panel, for your webinar control panel, you should see something that looks very similar to what I have on the screen here, which is a place to ask questions. To ask a question, simply type in your question and press send. We'll be able to see that question as staff, and Jocelyn, Anna, and I will be selecting from those questions, and we'll pose the questions orally to the speakers following their presentations. So rather than trying to raise your hand or unmute your phone, just please use the question toolbar, submit it to us, and we will help ask those questions. When I give the 5-minute warning, I'll probably also remind you, the audience, that it would be a good time to submit questions if you have them. So with that, I'm going to get out of the way and introduce our first speaker. Our first speaker is Gail Zedleski. Gail is a research assistant professor in the School of Marine Sciences at the University of Maine, and she'll be talking to you today about acoustic monitoring of fish and their interactions with the Ocean Renewable Power Company device. So Gail, when you're ready, and when Anna gets your PowerPoint presentation up, please take it away.
Well, thank you, Simon, and thank you, Anna and Jocelyn, for inviting me to provide this information. What I'll be speaking with you about today is some active acoustic monitoring that we've been conducting on the Ocean Renewable Power Company device, which is a tidal power device that I'll get into some details on in a little bit. But the talk is primarily focusing on fish and their interactions with the device, and trying to gain an understanding of fish in the area where the device will be deployed ultimately. I know the webinar has a focus on post-deployment monitoring methods, and mostly what I'll be talking with you about today are the active acoustic methods that we've been using prior to the actual deployment of the device. But we also had a great opportunity to look at fish interactions with a test device that ORPC used, and we'll be able to show you some of the results from that work as well. So next slide. So the outline of the talk that I will provide today includes going through a little bit of detail on the approach that we use to determine a strategy, or how we went about deciding what questions we would ask. And really, our focus has been to have an understanding of baseline conditions about the site where a device will be deployed, and also having a control site or a comparison site so that we have an area that's not impacted by a device, that we can understand effects and impacts of the devices on fish in particular. So with that said, the next thing I'll discuss are the near-field monitoring results that we've received using the test device that ORPC deployed. I'll also talk about the strategies that we're using to assess vertical distribution of fishes, which we believe is the most important baseline parameter to understand before these devices go in the water. And finally, I'll talk a little bit about strategies and techniques that we'll be using for post-deployment monitoring, but want you to keep in mind as we move through this that that all of the work I'm talking about is pre-deployment at this point. So next slide. Anna instructed us to be sure that we give you our take-home points right up front, simply in case Simon cuts us off before we get to the end. So here are my 4 points to be made at the beginning, and I'll come back to these at the end, hopefully. First, communication is key. We've done all of this work in collaboration and discussion with not only ORPC, but the agencies who will be involved in regulating the device and the areas that these devices will be going into. In terms of the interactions monitoring, we found it really important to understand or to think about when fish will be in an area to be able to monitor that area at the specific times that they'll be active. Third, baseline vertical distributions seem to be really important for understanding the risk of the potential interaction and understanding effects and impacts ultimately. And finally, we really think there's going to be no one-size-fits-all solution for monitoring these devices, and so I think there are going to have to be innovative approaches which could incorporate some of the things that I'll talk about today. So next slide. What I'll first talk about is, again, our approach to determining a strategy. So if you skip right to the next slide. We essentially had ORPC came to the University of Maine. Anna, can you switch to the next slide? Thanks. And you know, came up with an identified problem they want to deploy a device, and they understood that there will potentially be impacts to certain marine receptors, those being fish, and they came and brought that question to us. So if you click, I think, twice, and fortunately, if you click again, we had some money from the Department of Energy to think about this problem and how we would approach that. So we came up with an approach to answering the question about how we would go about determining what the impacts or effects of their device would be on fish in the aquatic ecosystem it'll be deployed. So next. We sat down with the federal agencies, and if you click again, the state agencies who would be involved in discussions around permitting a device, and said, this is the approach we think we should take. We know that this is going to be an open device where fish might be able to avoid the device. So we really have different questions than what you might ask if you were trying to permit a dam. So we brought the ideas of, and I'll get into the approach in a little bit, to the agencies, and they certainly had some of their own ideas, and we incorporated those into our projects. If you click again, after our first year of collecting data, we brought the data back to the agencies and discussed with them what further needs might be. And so we're really in this iterative process of understanding and developing our research to understand the impacts of the ORPC device in we can better understand how they might be impacted. Secondarily, as we kind of went around that loop or came back to the agencies, they identified the need of definitely knowing what the species were that might be interacting with the device. So, and ultimately, once the device is deployed, we really want to know how might the Tidal device affect the vertical distribution of fish in the water column. So that gets back to post-deployment monitoring, which I won't really get into too much here. So if you click to the next slide, our near-field monitoring work really is going to inform a lot of the work as we move forward. And just to give you an idea of the region that we're talking about, Eastport, Maine is the area it's the easternmost point in the United States. You can see the inset map there where it's located in regard to the state of Maine. And really we're talking about an area called Cobscook Bay. And what you see in this photo or in this image is the red shaded area is the proposed project site according to the ORPC's draft pilot license application. The green X indicates the pilot project site where a device would actually be deployed, and the yellow triangle represents the research platform where we were able to do our monitoring. So next. This is another schematic of the TIGEN power system of ORPC. It's going to be a bottom-mounted deployment, and you can see what the device looks like there. If you click again, there's an actual photo in the bottom right-hand corner of the research platform with one part of that, what's called a TGU system, that gets deployed below that research platform. And what I'm going to do is show you some of the monitoring that we did in terms of fish interactions with that test platform. Next. So on the research platform, we mounted two of these, what are fondly called acoustic cameras, or DIDSONs, that some people might have heard of. And the camera has, the picture there shows you the field of view. And if you click again, what you'll see is where the DIDSONs were actually mounted on the research platform and the view that actually allowed. And if you look at the green and the yellow triangles on the bottom right image, what you see is the view. We could actually see fish and various things moving into the field of view and the edge of the device foils. And so we could see fish interacting in front of the device as the tide moved one way and as they come out of the device as well. Next. So the data collected, well, the data that I'll present right now are data from 24 hours of footage, and it was in September of 2010. The data right now are sampled every other 15 minutes, and what were recorded during those times were fish size, their depth according to where they were in that view that I mentioned, and their behavior. So if you look at the graph in the bottom, the gray bars and white bars indicate data that were collected and data that weren't analyzed, or data that were analyzed and not analyzed. So again, we looked at every 15 minutes of data right now, and our intent is actually to look at all of the data. But what you can see is that we looked at data throughout 2 tidal cycles occurring day and night. So within the dashed lines from about 1900 to 0600 were during the nighttime period, so it was dark. So, so that's over the period over which we collected data. We also collected data during different seasons. So this is, I'm only going to present the data we collected in September. Next. So the questions we asked are, do we see fish around the turbine? When do we see them there? What are they? How do they behave around the turbine? And does the fish behavior change with day and night and fish size? You can see a video image hopefully on the right, and there's some fish that are actually moving at about 7 meters depth that are swimming away from the edge of the device, which is not turning in this image. Next. So in terms of when are the fish there, you see on the top panel.
Sorry to interrupt. You have about 5 minutes left, and for the audience, if you have questions for Gail, please, now's the time to start submitting them.
All right, I might have to talk a little faster. So what you'll see in this image in the bottom, if you look at the number of fish, we did see quite a few fish that interacted with the device, and you'll see that we saw them all times of the day, but 90% of the fish were seen at night, and lower numbers during other times of the day. But the time that we did see a lot of fish was at slack tide at night. You can see that peak there, which occurs around the slack tide. So if you go to the next slide, we separated the fish into small, medium, and large categories, and you can roughly look at, when we did physical sampling of this area and around the same time of year, you can see at least that medium-sized category are juvenile herring, likely juvenile herring, but again, these are acoustic images, so the sizes that I'll show you are related to the sizes that we pulled off of the acoustic images themselves. So if you go to the next slide. So the next question is, where are the fish? So what we see here is in the top, well, on the left you see the image of where in the view we saw fish, above the device, at the device, and below the device. And what you see on the right-hand panel are day and night numbers, and what you'll see on the night panel is that the numbers are about an order of magnitude higher than during the day. So we see a lot more fish again at night. And we see higher percentages at night at the device level, and mostly these are small fish. If you switch to the next slide. Our question was then, how do they behave around the turbine? And if you actually click 3 times through this, we had 3 different behaviors that we classified. Passing by, indicated by the green arrows, going through the device, the red arrows, and then actively avoiding the device as the blue arrows. If you go to the next slide. You see that these behaviors were seen both day and night, but what you see is that at night, more of the smaller fish actually went through the device. And what you'll see is that there's more avoidance proportionally during the day than at night. So next slide. So from the near field study, we saw that fish were mostly present, all the time. Most of the fish we observed were relatively small, and a higher proportion of the fish avoided the turbine during the day. Next. I want to make sure I'm able to tell you a little bit about our strategies for assessing vertical distributions. Next slide. And our strategy includes using downlooking at active acoustics at a baseline and a control site, and those are identified by the green and the yellow X and triangle respectively. We're doing this multiple times of the year throughout multiple seasons, and what we're doing, if you go to the next slide, is using the DIDSON again along with an echo sounder. It's actually a single beam echo sounder, and that's identified by the SIMRAD there. Next slide. And this just gives you an example of what these data kind of look like. But if you go to the next slide, our approach has been to focus on what's going on over a 24-hour period, simply because we think that the variability over day and tidal cycles is very important. And again, we're doing this over seasons, but we think it's more important to sit at the site of interest and understand what's going on with the vertical distribution of fish at that site. And this just gives you an idea of what we're doing. We're sitting in a location for 24 hours and documenting the vertical profile of fish in the water column. And we're doing several things to understand species at these locations. Next. And we're using volume backscatter, which is a relative index of fish density, and this slide gives you an idea of over a 24-hour period when we see the highest densities of fish. And again, slack tide at night, you notice a high number or relatively high density of fish. Next. And then we take these and we can actually look at these in terms of vertical distributions of fish and try to understand where fish are in the water column, day and night, ebb and flood tide, and in relation to the depth of the device. And this again is pre-deployment, but the red bar indicates where the device is expected to be deployed. Next. So with that, we hope that we'll have a greater understanding of the potential risk in that area of the water column to various different species. So in the future, next, our strategy for post-deployment monitoring is to incorporate split beam hydroacoustics so we can actually do three-dimensional tracking of fish around a device. And if you switch to the next slide, this gives you a schematic image of what the deployment will look like and our sampling methods. Again, using active acoustics, down-looking, which is identified by sites A and B, and we're going to have a split beam hydroacoustics, which is identified by C, that will be continuously monitoring. So A and B are 24-hour samples throughout the season. C will continuously be monitoring fore and after the device, depending on which way the current is running. So last slide is my take-home message again, which I won't repeat since I don't have much time, and then I'll finally finish with some acknowledgments. If you go to the next slide. Hopefully that gives me at least a minute to mention or to answer questions.
Actually, you did great. You're pretty much right on time. So you had, I see 4 questions for you, Gail, and the first one is kind of a nuts and bolts question. What is the scale and the rotational speed of the turbine?
The size of the, if they mean scale, do they mean size of the turbine itself?
Yeah, and I think perhaps your slide probably showed the best representation where you had the picture of the turbine deployed on the barge. So that might have answered the question.
Right. So it's approximately 6 feet in diameter, and somebody from ORPC might be on the phone and correct me here. And about, was it the one on the platform there is about 40 feet long.
Hey, Dale, Peter Stein, it's about 40 feet long and a good 10 feet high.
Right.
There. You can see the picture.
And then
there.
what was it? Was there a second question there? Oh, the rotational speed. So I think the tip speed ratio is about, what, 1.5? Or the optimal tip speed ratio.
Okay, that's fine. The second question.
Peter, do you have more information there?
Yeah, it's probably about it runs about a revolution every second is about right.
Mm-hmm.
A little bit slower actually.
And it's dependent on the tidal current.
Okay, great. Second question. Have you thought about how to detect differing behavior of shoaling fish, those attracted to underwater structures versus those that swim by?
So the way I kind of simplified the way we classified the behaviors there, and I don't know if we necessarily had fish that you would call shoaling or that would aggregate to that device. But we definitely saw schools of fish, and we saw schools of fish moving and avoiding or moving below the device or above the device. So we don't, when I mention that pass-by category, it's really fish that don't seem to be or have responded already before they get into our field of view, or aren't really responding to the device itself or the research platform. You know, we were really happy to see that as many images of fish as we did, because we were a bit worried about the fish avoiding the research, the whole barge altogether. So, but we did see a lot of fish moving by above the device that didn't seem to be responding to it.
Great. Third question, was the device platform lighted at night? Might that account for the greater presence at night?
No, the device was not lit at night.
Okay. And I have someone responded in a follow-up to, I think, the first question. Sean Anderton said that the device has about a 20 to 40 RPM rotational speed, just FYI.
Great, thank you.
Were there any fish kills observed, or were there only behavioral avoidance, such as passing through or swimming around?
We did not document any mortalities associated with interacting with the device. It would be somewhat difficult, based on you saw what the images look like, to be able to say what happens post of the view that we saw. We did see fish coming out of the device on the opposite side, and a lot of them, the ones that we did see, were relatively small, and we actually were able to see them orient in the wake that is developed behind the device and reorient themselves, and that's what that little loop was that I kind of quickly went by. But we saw fish reorient into the tidal streams and move then downstream from the area of view.
Great. And then last question while Anna loads up the next presentation. Did you detect signals that may indicate presence of other organisms, such as diving birds, seals, or other marine mammals?
No. I would only say we might have some indication of things that are smaller than fish, but we did not see anything that was larger. So we do get to see things like masses of krill and that kind of thing, but we did not quantify those types of organisms.
Great, thanks, Gail. And if there are any other questions for Gail, continue to send them. Just note that they're for Gail, and we can send them to her, and she can answer you in writing. So if you have any further questions, we can do that. But now I think we'll move on to the next presentation. So thanks, Gail. And the next presentation is Mary Ann Adonisio, who is the Director of Resource Assessments and Project Development for Verdant Power. She's been in that role since 2007. And she's going to talk about kinetic hydropower operational monitoring strategies and technologies for pilot arrays. So go ahead, Mary Ann. I will give you a warning in 10 minutes, and you'll have 15 minutes.
Very good. I hope you all can hear me.
You sound great,
Does that
Mary Ann.
work?
Yep,
very good. All righty. Can we move on to the next slide, please? I'd like to thank the DOE for giving Verdant the opportunity to present in this webinar. I'm going to take the discussion up a slightly broader overview of what really strategy means in terms of environmental monitoring as it relates to the advancement of this technology. And of course, sometimes I think we all feel that it might be the art of war. However, what we're really trying to do with these environmental strategies is devising a plan towards a common goal. And that is essentially what has been going on at the RITE demonstration project for the 4 years prior to 2009, when we placed the first tidal array of up to 6 machines in the water. And what we are proposing to do as we move forward with the RITE pilot project, which is currently in front of FERC for a license application. Next slide, please. So I think the common goal that we need to keep in mind and in the forefront of what we're doing here in terms of environmental monitoring is that we are trying to generate electricity in an environmentally compliant way. And to date here, the burden has been on the marine hydrokinetic developers not only advance the technology through the technology readiness levels path, but also provide project economics that will allow investors to invest in the technology as well as develop the project, and then the environmental burden of actually allowing for the permitting and the monitoring. On the regulatory side, of course, there is multiple stressors that need to be examined with anything that's placed in the water, but then balanced with that is a very large burden for renewable portfolio standards policy from the state and from countries as well that mandate that we integrate some kind of renewable portfolio into our electric supply. Next slide, please. So today's themes are array monitoring, what we've learned from the demo, the strategies that we are trying to match these techniques to the scales and proportionality of the risks associated, and some of our observations for the next generation of the questions that we feel really need to start to be looked at. I'd like to thank both NYSERDA, which is the New York State group that has been funding a portion of the environmental work, as well as our engineering partners, Klein, Schmidt, and Associates, for their work supporting us through the pilot. Next slide. So I think everyone's fairly familiar with the RITE project. The full body of work that was done during both the demonstration as well as our plans for the future project for the pilot license are available on that website. And I'm not going to go into great detail of what was done because I think most people on this have at least are familiar with the project. But the points are that the project was operational for 9,000 turbine hours. We had excellent technology operation, in other words, in terms of the electrical generation capacity of the Gen 4 machines, and that during this several-year period with several deployments, there were no observed adverse environmental effects. And that was conducted through the execution of 11 study plans with active acoustics during at stationary, mobile, and multiple deployments of transducers, as well as bird observations. And we need to remember, as some of the colleagues that have presented in past webinars, we have multiple fish species here, including 2 endangered species listed, but we don't have the marine mammals, which, of course, at different sites are being studied and the technologies being developed to examine marine mammal movement. But at the RITE site, that is not an issue. But we do have the multiple fish species. Next slide, please. So the Gen 5 machine, which is an adaptation from the Gen 4 machine to our newer machine, the 2 side-by-side comparisons are shown there on the left, is a staged installation of first 2 machines, then 3, then 12, and then ultimately 30 turbines in an array format. The machines are 5-meter machines. They are still the 37 kW machines, which are relatively small, which requires that there's multiple in an array, and the rotational speed on the rotors is 37 RPM. And so what we're proposing to do in this 10-year pilot is to conduct longevity and reliability, a cost reduction of O&M, and continue to prove the environmental compatibility. And so what we've proposed in the license application is a suite of environmental effects plans, which are progressive plans based on seasonal deployments of this equipment, and that all work together to try to understand what an array, the effects of an array function of the machine is. Next slide, please. So I want everyone to think about proportional risk here, and there's different ways to present this, but initially, the environmental community was very concerned about placing multiple machines in the water, and there were multiple unknowns and sincere concern of catastrophic risk associated in the fourth quadrant, the high risk and high effect. And what actually happened through the demo is a much lower actual observation of risk in the demonstration, as shown by the yellow dot. 6 machines operating with very, very minor, if any, effects. And therefore, we were able, working with our agencies, to move forward to be able to build on the knowns, that we know that there's a seasonal movement and abundance in this area, and that the zonal presence and avoidance of the fish in and around the machines, was apparent, and that we are able to observe mostly the machines in operation. And so as we move forward to a 30 machine, we're still operating under the assumption that the likely effects are going to be observed in that category 1. Next slide, please. And so this is some of the results. And again, I point you to the RITEproject.com for the full body of work that was done. But this was one of the key things that led us to be able to say that there is seasonal abundance and movement. The multicolored graphics are the fish events that we're seeing with the split beam transducers. The blue track is read to the right, and that's the tidal height difference. And almost exclusively, if you study this a little wee bit, you find that fish are moving when the tidal difference, when the waters are slower. And that's where you're seeing the abundance. It just makes sense, but it's really nice to be able to see it graphically. Next slide, please. So this was one of the key elements. The second element that we observed through all of the demonstration was the fish are primarily observed inshore and in the median zones, and there are limited numbers of fish observed when the machines were actually operating. So down in the lower right corner, you're showing a sinal curve of the tide curve in the area. Of course, the machines are operating in the red zones. When the machines are operating, we observe very few fish. And that was conducted based on the 24 transducer array that was deployed for the project, which slowly had an attrition rate down to, I believe, at the end of the project, I believe we had 4 or 5. I think 4 was the last amount of transducers, still producing good results. Next slide, please. And so building on this, one of the things that we've come up with is sort of a scaling that you are able to look at the machines around a machine, at and through the array as a deployed array of 10 tri-frames or 30 machines, and then at a much greater macro scale around the array and region. And so the agencies are still looking for us to understand the effect of the array in a broader area, and this is how we suggested to approach it. Next slide, please. And so what we're trying to do is continue monitoring the array, producing results, and then work through an operational monitoring concept that essentially monitors the operations and adjusts the monitoring. We'll be working in that quadrant with the agencies, as we've done throughout the demonstration process, with the understanding, of course, that if we start to see, as we incrementally add more and more machines, if we start to see true effects, that our next step would be to monitor, adjust our operations, and ultimately the ultimate safety net provided for in the FERC pilot license would be a stop and remove order. And so we're moving forward in a very progressive manner. We do believe that we would mostly see the activities going back and forth between monitoring the operations and in fact, adjusting the monitoring. Next slide, please.
In about four minutes, Marianne, and to the audience now is a great time to start asking questions.
Very good. So I'm going to have to speed up as well. So what we have here is a $2.3 million suite of 6 study plans that balance the monitoring of the environmental risk with the available technology. Key thing to remember is monitoring does increase when more turbines are operating. So next slide, please. And so this is the pattern at the various scales of the combination of fixed hydroacoustics, DIDSON, netting tagging, bird observation, which is quite easy at RITE because it is a shoreline-based deployment, not an offshore deployment, as well as a noise monitoring, which is largely for the turbine condition. Next slide, please. And I'm going to move through these fairly quickly because, again, all of this is available on the RITE-project.com. The 3 key ones is Micro-Meso scale using the DIDSON imaging. Essentially, we're going to use a stationary DIDSON aimed at the turbine in a seasonal period of about 3 weeks, observing fish activity not only on the bottom, but in 24/7 with the operating machine. Next slide. Our second technique involves some telemetry with detection of large, greater than 84 centimeter species, which are tagged by others. Next slide, please. And finally, at the meso scale, through the array, we propose to use stationary biosonic split beam transducers, very similar to what Gail had shown in one of her later slides, to actually observe in front of and in back of the operating machine. But again, this would be two of these split beam transducers deployed within the 10 tri-frames of the array. Next slide. And so what we're trying to do is, through the RITE demo, is that we tried to come up with a basic understanding, which was quite costly. And then through the RITE pilot, we reset the bar and started to come up with a strategy to observe the machines in an array situation. But again, it is still quite costly. The red line on this graphic represents the revenue. And so the monitoring costs still significantly exceed the power revenues expected from this size pilot demonstration. Next slide, please. And so as we move forward, there is a challenge of environmental monitoring, not only at scale, but whether the results can be transferred to arrays, and can the understandings that we're learning at sites be transferred to other sites. And ultimately, the goal has to be, can this environmental monitoring of arrays move to a reasonable cost level? At this point in time, Verdon's consideration is, we believe we have made some transference into understanding arrays, but our largest challenge now is still to understand the movement and the behavior through the arrays at the meso scale, and that's primarily what the RITE demonstration is hoping to accomplish. Next slide, please. Hello?
Marianne, are you okay? Is this not the correct slide?
No, that's good. 19's fine. So I really want to challenge some of the researchers and the regulators, is that we really start to have to think into this meso and macro scale of observation of techniques. Right now, we've been very focused on watching the individual machines at a very micro level. And as you can see, the DIDSON can look at the machine, but in a very, very narrow field of vision, as well as the split beam transducers. But the fact of the matter is that there are plenty of things in the water that have multiple structures in the water that have been operating for years. And so we really need to start to think, as we move forward, how are we going to monitor the environmental effects of a larger array. Next slide, please. Moving to 20.
Yes, around 20.
Very good. So the bottom line is that tidal energy is renewable energy, and if our goal is to generate renewable energy, we need to find this balance between the environmental monitoring requirements and the costs of that associated with the effects. And so I will conclude with the last slide, which would allow you to either contact me as well as go on the RITE site. My takeaways, if I have a moment on that previous slide, are let's try to remember the goal that renewable energy production can be done in an environmental compatible way. Learn from these early stages experiences at projects with monitoring to reduce the cost. Really need to start thinking in a risk-based framework to proportionally reduce monitoring in the future. Otherwise, there won't be an opportunity to move forward with this renewable, and begin to focus on array and site challenges drawing from other fields. So that's it. Thank you.
Great, thanks, Marianne. And we had just a couple questions for you, and I think that the questions you posed about micro, meso, macro are really excellent, and could be taken up in a, I don't know about addressed, but taken up by other speakers in this webinar too, so we might get to some of that. But the two questions I have for you specifically were the following. Let's see, the first one is, how are the continuous DIDSON data being processed?
Well, the DIDSON data is going to be taken over a seasonal period. We're hoping that the DIDSONal data would be run by 3 weeks or as long as 6 weeks, depending on how long the water intrusion and silt frame and the device can be placed underwater. The actual processing is a proprietary program that we are actually working on, which would be through Zone Trigger, and we're also working potentially with other screening programs that would allow us to be able to enhance the fish image. So it's not a real-time, it's real-time data collection, but not real-time analysis. All of the post-processing of the DIDSON data will be done, post-video collection.
Great. Second question, do sturgeon pass through the project area, and if so, will they be looked at?
To date, that was one of the big questions through the demonstration project. Is both the Atlantic and the short-nosed sturgeon are on the endangered list, and there was very little data. There was no observation of that particular species through the project site, and so the agencies requested that we deploy these receivers. These VEMCO receivers, which we've done here this season, and we're attempting to locate tagged species. And so through the last 70 days of data, we have seen one tagged sturgeon pass through the site.
We have time for one more question.
That's really a long-term macro scale kind of study that is going on at the site.
Great. We have time for one more question. I see two more on my screen. One is asking you to elaborate on the before-after control impact recommendations on your takeaway slide, and the second one is more nuts and bolts around that you had mentioned that you deployed 24 transducers with your first 6 deployed units, and only 4 of them worked in the end. What were these, and do you know what caused their failure? I think that the before-after control impact question might be a little bit bigger for the 1 minute. So maybe if you can comment on equipment failures, what caused those, and how you dealt with it.
Yeah, the transducer array was a 24 transducer array that was intended for continuous operation up to 12 to 18 months, and we actually ended up getting a little over 2 years worth of data. So the decrease of the transducers was simply because we frankly didn't maintain them. We just put them in and let them operate until they, it was too costly to go in and maintain them. So we just allowed them to operate as long as they did. The real big takeaway from that was that 24 transducers gave you a lot of data, but practically, in a practical sense, one transducer or two transducers is going to give you the same answers. So the array situation at RITE probably will not be repeated. Less transducers gives you about the same kind of understanding of presence and abundance. And so that's the good news.
Great. And maybe while Anna loads up the next presentation, if you want to make a comment on Baki monitoring, feel free to do so. And if you'd rather hold that for future discussion, that's fine too.
Well, again, this goes back to the original concept when we approached the agencies in 2003 with how we're going to monitor these machines. The concern is that what's there and what kind of changes we're going to see. With one or two or six machines, it's simply at the scale, at this 5-meter scale. You're simply in such an energetic environment. You're just simply not going to see, a radical change, and that was proved out in the RITE demonstration. We attempted to see changes in hydrodynamics and changes in fish patterns, and because it's such a minute change that's probably being caused just simply by the energetic flow of the water, it was very difficult to actually measure a change in environmental effects. And so that's sort of a radical concept, I understand, for people to take a threshold event that we really should just be watching these operating machines, because that is the condition that we're going to see with Tidal deployments. And but that's essentially where the agencies, at least in New York, are right now. Is let's get the machines in and operate and see what's happening with operating machines.
Great. I'll cut you off there, Marianne. Thank you so much. Great presentation. And I'll introduce the next speaker. Actually, the next speakers, David Ainsworth, Project Manager of Marine Current Turbines, and Frank Fortune, Technical Director and Marine Biologist for Royal Haskellning, are going to discuss lessons learned at the world's first commercial-scale tidal turbine, CGen, in Strangford Lough, Northern Ireland. So David and Frank, take it away.
So I'm David Ainsworth. I will just give you a quick 3-minute overview of CGen and leave you then to 12 minutes of Frank to talk about the environmental impacts of CGen. So next slide, please. So MCT's history, basically, CGen is MCT's third scale evolution in their tidal development program. We go back to about 1994, when we installed a 15-kilowatt proof of concept device in Lough in Scotland, which proved to be very successful and led to a whole load of investment and policy change by the then DTI to actually encompass tidal energy as a potential source of energy for the future. Next slide, please. In 2003, we installed a 300-kilowatt proof prototype device, Seaflow, in the north coast of Devon in England. This was eventually decommissioned in October 2009 after achieving all of its objectives. There was a 300-kilowatt device, 11-meter diameter rotor, was not grid connected. It ran into a low bank on the device, but basically proved all of the fluid dynamics and proof of concept for the whole system, really, for the evolution to the next technology, which is the 1.2 megawatt CGen. Next slide, please. This is a typical day in Lynmouth, North Devon. As you can see, it's a very wave-exposed location. It's exposed to the southwest. And what we achieved in 6 years, at Lynmouth, we've actually achieved in 3 months at the next site. Next slide, please. Which is a typical day in Strangford Lough in Northern Ireland, where we actually have 9 knots of current, very low wave climate, and very interesting, lots of variation in environment and indigenous species. Sorry, next slide, please. So the CGen, basically subsea, it looks like this. We've got what looks like a wing with two 16-meter diameter rotors on each end of the wing. Each one of the drivetrains is 600 kilowatts and can be run totally independently. The structure sits on the seabed on 4 feet and is held to the seabed via a 1 meter diameter pin pile. So the whole structure effectively sits on 4 1 meter diameter pin piles. It's got a very small footprint on the seabed. Next slide, please. The system was actually installed on the 1st of April 2008, and it was installed using what is probably the world's largest crane barge. There's not too many of these assets in the world, so if you design your installation process, don't design it around using these crane barges because it's not a good idea. The whole positioning of CGen on the seabed went bang on. It was actually positioned within 10 centimeters of the target location, and that was a good job because we actually had pre-installed the power cable to the structure. Next slide, please. So during the installation process, we actually used the structure to actually drill the pin piles into the seabed. As you can see on the left-hand side, the yellow structure is actually a pile-top drilling rig sitting on top of a conductor tube. The pin piles, like I say, were about 1 meter diameter and embedded in the seabed 7 or 8 meters. We actually managed to install each pin pile, or do the drilling of each pin pile in about 8 to 12 hours. The pins were then just dropped into the holes and grouted into position. Next slide. As you can see, one of our benefits is that we can actually raise the whole of the operational components to the surface and actually maintain these using the very low cost intervention boats. We don't actually have to drop any anchors on the seabed. We just tether the boat to the structure. We can actually use the onboard crane to actually remove blades. We've done drivetrain changes. We've done blade swap outs. And we can do all of the operation and maintenance very, very safely in this environment. So as a R&D site and an R&D facility, this is an excellent location. Next slide, please. One of the other benefits about CGen is that most of the energy in the water column is actually in the upper 50% of the water column. So with CGen, we can actually position the drivetrain effectively in the area where we're going to maximize the energy capture, which when you're looking at economic sites and the economics of projects, it's very, very important. Okay, next slide, please. So there's another picture of CGen. There's the guy actually boarding the structure here is a very well-known BBC TV presenter, making a documentary. But sorry, just to wrap up. So CGen, like I say, installed in April 2008. Now been operational for 3 years. We've got over 4,000 operational hours experience on it. We've generated over 3 gigawatt hours of electricity into the grid. We've got a whole raft of environmental data from everything from porpoises to seals to benthic communities to impacts on birds. And Frank will now take over for the next 10 minutes, hopefully, to actually give you a summary of where we got to with the environmental situation.
Wow, David, that was a bit of a whirlwind. I hope I have enough slides to keep going for the next 10 minutes, and I thought you were going to be a bit longer. Okay, so that's just a quick slide introducing myself. I've been involved in the CGen project since 2004 and currently involved still in the post-installation monitoring and looking at other sites for MCT as well as a number of other wave and tidal projects across the UK. Right, next slide, please. Okay. I'm going to go to the reasons why we are monitoring and also have in place a number of active mitigation measures for CGen. Obviously, we're all familiar, or those of us that work in that field are familiar with environmental impact assessment. We went through that process in 2004, 2005 for CGen as a support to the licensing application. The key things that came out of the EIA process were a couple of very major questions to do with common seals and to do with rocky reef. We were interested in changes of pattern of use of the area as a result of the installation of the device and the operation of the device. Key to that really is whether they were, one, disturbed, and two, actually being hit by the rotors of CGen. We were also interested in the reef structures that the device is fastened to. For a bit of context, I haven't included a slide on this subject, but Strangford Lough is an internationally designated site for its seal population and also for its rocky reef environment. And CGen is actually fastened to some of that rocky reef, so that was a major focus. And there are seal colonies a matter of hundreds of meters away from CGen. Next slide, please. Okay, so I will not go into the legislation because it's very UK and in particular Northern Ireland specific, but coming out of the license application, a license was granted, but a number of conditions were placed upon that. Key ones were mitigation measures, and these related to presence of an active observer, a human observer on the pile with the ability to shut down the device on approach by basking shark or seals or cetaceans. That led to daylight operation being a necessary criterion. And in parallel to the MMO operation, we also ran an experimental active sonar deployment to find out whether the active sonar would be a useful replacement for MMOs. The work of the various streams of monitoring and mitigation have been passed on a regular basis through an independent science group made up of regulators and advisors to allow us to gain as much advice and support from a wide range of experts in this field. Okay, moving on please. So looking at the mitigation, here we've got a picture of a marine mammal observer on the device, looking upstream, looking through a spatial grid on the fastened to the side of the device, gathering qualitative data on mammal activity and their behaviour close to CGen, working to calibrate the active sonar system that was working in parallel, and with the ability to shut down the device. We initially started out with a shutdown distance of around about 200 meters, so any animal coming towards the device within that that area would lead to a shutdown. We quickly learned that we could shut down the device very quickly, and that distance was decreased gradually on the advice of the science group, and we ended up with an action distance of around about 50 meters. Okay, and we ceased using MMOs in 2009, and the mitigation for potential collision with seals and cetaceans and basking sharks was taken over by the active sonar. Next slide, please.
Frank, this is Simon. About a 5-minute warning, and audience, start asking your questions now, please.
Brilliant. Okay, so mitigation, we've got active sonar going on here. We can detect animals out to 50 meters, but we actually have we can shut down the device if we get a positive result into 30 meters. Very low number of precautionary shutdowns. We can track animals. We also get a number of false positives though from drift material as well. There's no evidence in significant change in marine mammal activity at night in comparison to daytime. Next slide, please. Okay, so now moving on to the monitoring that came out of...
Frank, are you still on the line? Frank, I think we may have lost you.
Yeah, I'm not hearing Frank. David, is there any way?
Yeah, okay, I'll just pick up. So marine mammals, yeah, we've managed to do things like aerial surveys using helicopters with infrared cameras. We've actually done 3 seal tag deployments using GPS and GSM tags. We've got 3 years pre-installation and 3 years post-installation visual surveys shore-based. T-pod monitoring for harbour porpoises, and also we've got the shore-based ornithology stuff. And then benthic monitoring, we've actually put in some SBLs to actually position some dive sites, so we can actually do repeated dive surveys on exactly the same location and actually look at the benthos on those areas. The last report that we're working on at the moment. Sorry, next slide. Right, so, and also when CGen, during the first couple of years of operation of CGen, we actually had marine mammal observers mounted on the pile who were actually looking at seals within close proximity of the structure. We used that to actually calibrate the sonar in the early days to actually, so we could actually get we could actually get a level of confidence with the initial sonar operation as mitigation. And that verification actually helped us to actually remove the marine mammal observers from the pile. And we now monitor the sonar vantage
points. Sorry about that.
Yeah.
David, I'm back.
Okay, you can have that one then.
Thank you. Okay, vantage points. Sorry about that. I seem to lose internet connection. So vantage point survey since 2005, all times of the tide. We did some calibration across different sides of the loch from 2 vantage points, but the bulk of the data was collected from 1 vantage point. Can we have the next slide, please? Okay, the telemetry data and also the aerial data, fixed wing surveys of both Strangford Loch and the wider surrounding area of Northern Ireland. There are trends showing a decline in common seals across Northern Ireland and the UK and Europe. That trend is followed within Strangford Loch, but nothing specific to Strangford Loch. The telemetry, we use GSM tags with 12 animals tagged at the 3 periods shown. We've clearly shown there's no barrier effect, and analysis of the data and a number of assumptions have allowed us to estimate that each seal in the population may pass within 20 to 25 meters of CGen up to 4 times a year. Next slide, please. Okay, in addition, obviously one of our concerns was the possibility of collision, so we had to work on the basis that this might potentially happen and have some measurements in place and some actions in place to collect evidence of that. So any strandings, there's a post-mortem measure in place. There have been a number of carcasses washed up over the years, as there have been before CGen was installed. There's no evidence of any egg interaction with CGen, and the majority of the dead animals have been as a result of fishing incidents and other types of activity. In addition, we've also had T-pods in place which are detecting harbour porpoise clicks, and they've also shown no barrier effect. They continues to be use of the narrows and the inner loch by harbour porpoise. And interestingly, building on what Verdant was saying, the T-pods are also reaching the limit of equipment life, and basically we're having a large number of failures now. Next slide, please. Okay, benthic ecology, we collected data using broad-scale mapping using multi-beam swath bathymetry. That allowed us, after ground truthing with video, to then map the biotope types on the seabed. We've also, at a number of fixed quadrats, collected data using video and diver observation, which has allowed us to monitor the seabed for any changes in the wake of the device, and we've observed no changes apart from natural change. Next slide, please.
Just let you know, Frank, about a minute would be great to finish up.
Well, that's me. Hi there. I was storming through the last bit because I wasn't sure quite where we were, so that's me finished. So if anybody wants to come at myself and David with questions, I'm more than happy. Great. Yeah, we have about 5 questions submitted here, so I'll wade through them and we'll see where we get. Yeah. First question is sort of a big one. What of the lessons that you have learned are considered transferable to other devices by regulators? And I guess that would be transferable to other devices perhaps in the UK and perhaps in the US as well. Interesting. Okay. David first.
Yeah, I think some of the lessons that we've learned are probably highly device specific. Because I think each device has got different characteristics. Like, we've got 2 turbines with 2 blades, and the potential for impact is probably lower than if you've got 3 blades and a larger turbine. I think it's without. I mean, we haven't actually looked at that in detail, but I think there's some of the data you may be able to transfer. But the way we're looking at interpreting this data is actually to support us and to actually do modeling, to actually look at the impacts on arrays rather than other devices.
I would also add probably the biggest one that might be transferable is a fairly obvious one in a high energy environment like this, where there's a lot of natural change, particularly for the benthic ecology. We've shown that you can't pick up any change other than natural, and that's not particularly unexpected. But it was something that the regulators wanted to see for themselves, and I think we've shown that quite clearly. We've also shown that, not surprisingly, seals are aware of their environment, as are cetaceans, and can manage their way around it quite well.
Great. Second question, you may or may not be able to answer this, but what was the total cost of the monitoring plan, and has the value of that been realized?
David.
I mean, when you look at, we've actually done an assessment. If you look at the complete cost of all the environmental stuff, including the EIA, including all of the mitigation, and including third-party research and investigations that were done on CGen, we probably spent it in just under £4 million, which is what, $5 and a bit million on environmental monitoring since 2005.
Great, thanks for sharing that. Next question, has there been any thought to monitor the turbine and marine mammal activity without shutting down when an animal is observed within the 30-meter zone? So do you let it keep spinning and monitor the results ever, or have you thought about that?
We're putting a proposal on the table. I mean, the problem we have, this is a highly designated area, and the seals in the area and the porpoises in the area are European protected species. So we have a risk-averse regulator, and I'm sure he won't mind us calling him that, who really needs some reassurance that there is not going to be any negative interaction before he approves that process. Now, we're working up all of the data sets we've got. We believe that we've got a very high level of confidence that that isn't going to happen, but we're putting together a strategy where we can actually work towards that. I think if you ask us that question again in, what, 6 months, Frank, we'll be able to give you an answer?
I think so, and it's worth noting as well that we went in, I mean, CGen was installed with fairly significant levels of mitigation in place, and we've managed to progressively remove that mitigation as we've demonstrated through the monitoring program that we're not having significant adverse environmental effects. But that question is bang on the money. I mean, basically that's the objective, and we are holding the hand of the regulator to give them the confidence to allow us to take that step, and we're hoping they'll do that very soon.
Great, thanks for that. 2 more questions. This one, how is the turbine braked? Is it mechanical or electrical? And what is the effect of repeated shutdowns on the turbine?
Right, well, the turbine, we actually have a pitch control system on the device. So the first thing we do is we drive the blades to neutral drive, so it doesn't actually extract any energy. And then the speed just naturally drops, and when it gets to a speed around 2 or 3 RPM, we can start applying the disc brake to actually slow it down further. So we can actually go from full speed to completely brake speed in a matter of seconds, which is very, very quick. And no, repeated braking doesn't damage the structure. The biggest issue we have is coming back online again, where we actually have we don't have a compliance problem, but we can actually get back online and offline very, very quickly with the grid. But the grid doesn't actually like 1.2 megawatts dropping in and out as quickly as we do. But they seem to so far have actually been able to accommodate us.
Perfect. And last question while Anna gets the next presentation up. What kind of sonar system was used to replace the MMO, the Marine Mammal Observer?
It's a system manufactured in Scotland by a company called Tritech. The device we've got at the moment is a scanning sonar, but we are currently trialing a multi-beam sonar with mammal detection algorithms being written around that as well, and we seem to be having some very, very good success with that. So if necessary, we hope that we can actually automate that as a process in the future for potentially monitoring on sites in the future if necessary.
Great. Well, thanks, David and Frank. That was, I think, our first successful tag team webinar presentation. So you guys pulled it off even with technical difficulties. So thanks so much. And we'll move on to our next speaker.
Thanks, everybody.
Thank you.
And the next speaker will be Brian Pelagi, who's a research assistant professor in mechanical engineering at the University of Washington, also affiliated with the Northwest National Marine Renewable Energy Center. And Brian will be talking about the long title, Integrated Post-Installation Monitoring, a discussion of post-installation monitoring for marine life interactions, acoustics, water quality, and inflow velocity on a tidal turbine, including the development pathway for a new stereo imaging system. So Brian, please go ahead.
Thanks, Simon. I'll try to make the talk a little less convoluted than the title. What I'm going to be talking about today primarily relates to the monitoring of a proposed open hydro project in Northern Admiralty Inlet with a site developer by Snohomish PUD. Simon, if you go to the next slide, please. Just to orient you to the site, we're back in the U.S. We're now on the west coast, and the proposed deployment site is in Northern Admiralty Inlet of Puget Sound. Admiralty Inlet is the primary connection to the Straits of Juan de Fuca, and all of the exchange that passes into Puget Sound on each tidal cycle passes through Admiralty Inlet, which is why it's a good site for tidal energy. The relevant features for the site are that the water is 60 meters deep, or about 1 kilometer from shore, which means that it's going to be very difficult to, or nearly impossible to service the deployed device using divers, so everything has to be done using ROVs or surface vessels. The peak current velocities are about 3.5 meters per second, so all of the equipment needs to be designed to survive those sort of conditions. There's a relatively low turbidity in the water column, which will come back when I talk a bit about the use of stereo imaging to monitor the turbine in operation. And then finally, there will be a cable back to shore, so we will have power and data capability rather than having to rely on standalone instrumentation. The turbines that are being deployed is Open Hydro's technology. The plan calls for the deployment of 2 6-meter turbines, 250 kilowatts peak power generation. These will be deployed on a gravity foundation in 60 meters of water for 3 to 5 years as part of this demonstration project. Next slide. So when we think about why we're doing post-installation monitoring, at a pilot scale, we're very interested in trying to provide information about high significance, high uncertainty interactions of marine life with devices. This is a key input to risk assessment frameworks to help really drive down onto what we really need to be concerned about as we move from a pilot scale to a commercial scale. In thinking about how this monitoring is conducted, we need to make sure that monitoring doesn't change animal behavior nor affect device operation in order to be effective. And then finally, a point I'd like to make is that environmental monitoring costs should not dominate over the other project costs at this stage. All of these projects are also demonstrating technical readiness and economic viability, and it's important to not lose sight of the fact that most of these projects are technology prototypes. So clearly, as we think about what we should monitor post-installation, there's a bit of prioritization required. Next slide. So in thinking about how to prioritize some of these concerns, I'm showing here a general output from a workshop that a number of you participated in 2010 related to trying to understand the potential environmental impacts of tidal energy. And out of the workshop, we created these summary matrices for commercial scale effects where the shading of a given box denotes the potential significance, where green means low significance, red means potentially high significance, and the number of triangles denote the uncertainty associated with that significance. And what you see here is at a commercial scale, all of the interactions that are potentially of high significance also have extremely high uncertainty. And so when we think about the point of pilot projects, we should be trying to address to the extent possible these high uncertainty areas. That being said, not all projects can have any chance of really monitoring all of these potentially high significant interactions. And so the areas that are outlined in a blue box are the ones that are likely to be monitored as part of this Snohomish PUD open hydro demonstration. You'll note that there's no plans to try to monitor cumulative effects. That's very difficult to do at the pilot scale, nor to do any monitoring of energy removal, which is also probably immeasurable at the pilot scale. So next slide, please. So of the potential environmental concerns, we get back to the question of dynamic effects, namely blade strike, as it's one of the few mechanisms by which you can envision direct injury or mortality as part of one of these projects. The objectives of this monitoring are to quantify the risk of blade strike to marine life and improve the understanding of how marine life responds to device presence. The challenge is that because regulations are written at a species-specific level, both of these types of monitoring should be carried out to the lowest level of taxonomic classification possible. This brings up a couple of challenges. The first is that laboratory and field studies to date suggest that blade strike will be an infrequent occurrence, and if it does happen, the outcome is not always of high significance. The other challenge is that this sort of monitoring is very difficult to conduct, and it's resource intensive, given that you have limited frequency of interaction coupled with a relatively high cost to perform the monitoring, which is why not all tidal projects that have been deployed to date have actually taken on this type of monitoring specifically for fish. If we think back to what David and Frank just went through, fish monitoring was not part of the MCT project. The regulator concluded that there were higher priorities and that not all projects could monitor all things. Next slide, please. So in thinking about the type of monitoring technology to employ to look at blade strike, we thought about a number of different types of monitoring technologies and converged on underwater imaging, which is, in our opinion, the best, though not perfect, solution to look at this. And we evaluated the different technologies along the lines of prior experience in the MHK industry of using this type of technology to address this sort of a question, the technology's capability to detect blade strike, the degree of taxonomic classification possible, the functional range, and the potential for behavioral disturbance. And so the underwater imaging has been used previously by Open Hydro at the European Marine Energy Center to study fish and marine mammal interactions with that turbine. In our opinion, optical imaging has the best chance of actually seeing if blade strike has occurred. Depending on the contrast, a high level of taxonomic classification is possible. Depending on the turbidity and aeration in the water column, the functional range can be on the order of several meters. And the behavioral disturbance, if there's no illumination required, is quite low, but in our case, given our water depth, illumination is required, and so there is the potential for behavioral disturbance associated with that. We also consider the use of active acoustics, though as you saw in Gail's presentation, it's difficult to discriminate really what's going on right around the turbine. At a fundamental level, the hard acoustic return from the turbine structure itself reduces the ability to distinguish between a near miss and contact. Taxonomic classification in the absence of other information can be challenging, though the functional range and the lack of behavioral disturbances are definitely a benefit over underwater imaging. Briefly looked at trawl surveys. In our understanding, no one has tried to use trawl surveys to look at blade strike, primarily because, as John Horn will speak about next, it's very difficult to trawl in these environments, much less directly around a turbine. Fish tags, which have been used at a couple of different projects, are not suitable for detecting blade strike in this location because you can't collect the tag fish after they've passed through the turbine, though tags certainly do provide a high level of taxonomic, not to mention individual classification, with a good functional range and low behavioral disturbance. They're a great tool, just not a great tool for evaluating blade strike. Next slide. So in thinking about how we were to pursue underwater imaging, we very early on decided to pursue a stereo imaging system whereby you have two cameras with an overlapping field of view, and by rectifying these images you can extract information about the absolute size, position, and speed of your targets, which was considered critical to the question of species identification as well as discriminating between strike and near miss. This is not a new technology. There's a number of similarities to ground truthing trawls and benthic habitat surveys. In both of those cases, there's high relative motion between the camera and target. The cameras on a hydrokinetic structure would be fixed. The targets would be moving quite rapidly. And in both of those applications, taxonomic classification is required. Uniquely for turbine monitoring, we have to think about how the lights and cameras are positioned relative to the turbine to provide imaging of the turbine without interfering with the inflow to the turbine rotor. Deployment times are much longer, on the order of months. And as a consequence of this, there has to be some mechanism to recover and redeploy the instrumentation. As I mentioned previously, we're in 60 meters of water here, so this has to be done without the use of divers. Next slide. So in thinking about the camera and optic selection, it really comes down to a question of how much resolution you can achieve. And the maximum resolution you can achieve is limited by the bandwidth of data that can be reasonably taken off from the project. And so we converged on the use of 2 megapixel machine vision cameras. These are commonly used technology in industrial settings. We're using a 45-degree field of view lens in air and a flat optical port for reason of biofouling. What you're seeing there is the camera. It's a Manta G201 with a Navitar lens to scale in the palm of my hand. So very small piece of equipment, but when you start thinking about how to integrate it into an overall monitoring system, you'll see it gets a little larger. When I talk about resolution, the big question here is if you're trying to make a species-specific ID, the number of pixels per target really matters. And what you're seeing here is a progression of images downsampled of a Chinook salmon prepared by Cressmer Williams, one of the people involved in this project from the Alaska Fisheries Science Center. And you can see at 500 pixels per target, you can make that species ID, but as you get down to a lower resolution, say on the order of 60 pixels per target, you can probably tell it's a fish, but beyond that, you're not really even able to make a genus classification. So the reason that we can't go with infinite resolution is that we need to think about how to actually manage the amount of data coming off of this stereo camera system. So next slide. I mentioned that we need artificial illumination at this site due to the water depth, and in thinking about imaging fast-moving targets, there's two considerations. One is that there has to be a very short exposure time on the order of microsections, and you need to achieve the largest light-to-camera separation possible. We're using full-spectrum strobes for this project, with 4 strobes per stereo imaging system. The reason we're using strobes is that the exposure times we're talking about to achieve good contrast with limited blur are too fast for a mechanical shutter, so it has to be a strobed illumination system to get the clarity of image required. The behavioral disturbance associated with the strobes is certainly one of the most problematic aspects of using this sort of an imaging system. We did consider the use of red lighting, IR lighting, and near IR lighting, but the reduction in effective range for the system is quite severe. And we determined early on that trying to use anything other than full spectrum illumination would probably not provide the depth of field and range of view we require for this sort of monitoring. So initially, there's going to be a preset duty cycle for this sort of illumination with analysis of the data coming back to look for indications of behavioral disturbance, either attraction or avoidance. As behavior of fish and interactions with the turbine are better understood, we like to progress to event-based or triggered illumination. Now that's potentially not going to be part of the initial deployment. Next slide.
About 3.5 minutes, Brian.
Okay.
And audience, please start submitting questions.
Okay. So as I mentioned, one of the challenges associated with marine energy is with the marine energy deployment of this camera system is the long deployment. Biofilms will start forming immediately after deployment and over time will degrade the functioning of the optical system. For this reason, we're pursuing 3 different types of mitigation for biofouling. One is a mechanical wiper, which sweeps across the face. That's what drives the requirement for a flat rather than domed optical port. We're also going to be putting a copper ring around the optical port, which has biocide properties. And then we're considering the use of ultraviolet lighting inside the camera housing, which may have the effect of reducing biofilm formation. Though even with this mitigation, performance will degrade over time and maintenance will be required. Next slide. So what does this all look like when we think about putting this together? So what you're seeing here is a conceptual layout of the stereo camera system. We're talking about 2 stereo camera systems being deployed for monitoring. One camera system will look across the turbine rotor. That is the best chance of getting a lateral image of a fish, which is your best chance for taxonomic classification. A second camera system would look at the turbine face, which has the best chance for strike detection, but the worst chance of taxonomic classification. So you're seeing here a compact frame that includes each system consists of 2 cameras, 4 strobes, and 1 main power and communications bottle. The whole frame is about 1.5 meters by 1.5 meters in characteristic dimension. So even though the cameras themselves are quite small, when you think about putting the entire package together, it starts to become a little large. The reason we're pursuing this kind of compact frame concept is for reasons of maintenance. So next slide. There's a number of reasons that you might want to recover and redeploy a camera system. Biofouling removal, as I mentioned, maintenance and repair due to ordinary wear and tear in this sort of energetic environment, potentially adding other instruments to the package, and reorientation of the cameras. So this whole package has to be recovered independently of the turbine because the turbine's likely down for 3 to 5 years, and the camera system is going to require maintenance every 3 to 6 months. So getting it back to the surface isn't so much of a trouble. The real challenge is getting it back down in the same location and reconnecting it to the turbine power and data systems. And so one of the concepts we're considering right now involves putting this compact frame on a cylindrical, basically collar that then would be lowered from a surface vessel and would mate with a mounting and alignment frame on the turbine structure itself. So this is one concept we're pursuing that might be used for redeploying the system, and you can see the relative scale of the monitoring system compared to the scale of the turbine. Next slide. So we think about integrating the entire system. If we start at the upper left, we've got the stereo imaging system. We've got the stereo imaging system looking at marine life and potentially the condition of the device as well, tied back into a junction model. We're also probably talking about integrating conductivity, depth, and dissolved oxygen sensor, which would be monitoring water quality. And then we're building in expansion capabilities for additional instrumentation. That whole part of the system has to be able to come back to the surface and be redeployed. That requires a wet-matable power and fiber disconnect. Those are extremely expensive, talking about something on the order of $70,000 per connector, with an effective number of connect and disconnect cycles of about 10. So very expensive equipment with a relatively limited use life. So this is quite technically challenging. Down on the turbine structure itself, Doppler profilers to measure the wake and the inflow conditions would be hardwired into the frame for the life of the project. Similarly, a hydrophone array looking at monitoring marine mammals as well as device noise would be hardwired, and we're thinking about, again, an expansion port there for other permanent instrumentation. That main communications and power system has a split to the turbine health monitoring systems as well as the power cable back to shore, which is how all the power for the instruments is coming from and all the data is going back. So next slide. So final discussion points. One of the things that I've wrestled with a bit as we've gone through the project is how much emphasis should be placed on monitoring for blade strike, given that laboratory tests suggest this is a relatively low consequence, low frequency occurrence. And as we do monitor for this on operational projects, how long do we do this before, how much species to species, site to site, and turbine to turbine variability is there before we can say that yes, this is an issue, or no, this is not, and we should move on to other considerations. A major challenge here is that the regulatory mandates are site-specific, but this very much limits the tools available, specifically when we look at blade strike. Another point would be that environmental monitoring infrastructure is expensive and should be leveraged whenever possible. So, for example, the stereo imaging system that we're deploying to look at marine life interactions can also monitor turbine health, looking at biofouling over time, as well as vibration of the structure. And then finally, post-installation monitoring is essential. We all want this data, but it's very technically challenging and costly to collect, and so prioritization of data collection is required. Not all projects can collect all types of data. So that wraps up my presentation. The final slide, just to acknowledge the number of people involved in this project. We've got a number of organizations and institutions and people involved, and all this work is supported by the Department of Energy and Snohomish County PUD. So thank you.
Perfect. Thanks, Brian. We have time for a couple questions. I see 3 on my screen. So first one. Question about strobes, using strobes versus constant light. Why strobes? Won't that cause startle response in fish?
So the strobe exposure duration is about 5 microseconds, about 10 microseconds. And the reason we have to use strobes rather than a constant light is that if you have a constant light on and you're collecting images at a few hertz, you get a lot of blur in your image. And as a result, it's very difficult to do the stereo camera rectification. And you also lose the ability to contrast the difference between something like a strike and a near miss at the turbine rotor. So the clarity of image really requires strobes, which is what's used for trawl surveys and benthic habitat surveys as well.
Perfect. Second question, for blade strike, did you consider using or mounting accelerometers or using accelerometers mounted on the blades?
There's certainly some consideration to other methods aside from video for detecting blade strike. It's possible that there may be an acoustic signature, in which case the hydrophone array could detect it. One of the issues associated with instrumenting the blades, however, is that if you think about the way the open hydro turbine is designed, getting real-time information off of the blades would require a slip ring of the same diameter as the entire turbine. So for this case, we'd be talking about a 6-meter slip ring, which means instrumentation on the blades, especially for some sort of real-time detection, is rather problematic.
Great. And last question while Anna boots up the next presentation. Have you looked at using software to automatically identify a fish species, or will it all be done manually by biologists?
Initially, manual detection by biologists, but long-term, the idea would obviously be to move to software detection.
Perfect. Brian, you're a half minute under, so thank you for that. Great presentation, and we're going to move on to the next one.
Thank you.
So our next presenter is, excuse me, get my sheet out, John Horn, who is a professor at the University of Washington School of Aquatic and Fisheries Sciences, and also does work and conducts research for the NOAA Fisheries Science Center at Sandpoint. And John will be talking about characterizing biological communities at marine renewable energy sites. So John, go ahead.
Thanks, Simon, and thanks, Anna. Hello, everybody. I thought we'd start with a bunch of faces because we're not having live video. Here are just some of the members, the people that are involved in this project. And what I'd like to do today is to take half a step back and think about how to monitor biological communities in these or at these proposed sites, and then use the Admiralty Inlet project that Brian has introduced us to as a case study almost. And I'll go through a little more detail later on who's all involved and the different types of data streams that we're trying to capture. Next slide, please. So as a biologist and being introduced to this community, from the engineers, I heard a lot of the impact on the devices, the strikes or impingements, and I'd like to change the perspective a little bit and put out that it's just as important to think about the impact of the devices, whether it be a single device, an array of devices, or an impact on an area. Next slide, please. Anna, can we get the next slide, please?
John, I'm flipping. It's not broadcasting. Let me try one more thing.
Okay, well, that's coming up. In sitting and thinking about what are the general challenges for biological monitoring, I came up with 4 points. First, sampling in high-flow environments. Secondly, the choice of sampling instruments and survey design. Third, detecting change and causes of change. And finally, the issue of scaling up, which we've already discussed and heard about briefly from Marianne in the Verdant project.
John, it seems like we've lost connection somehow, so just give us 1 second. Sorry about that.
Okay, I've got a message here saying my network connection's been restored. Can you hear me?
Yes, we can hear you. Okay, hold on.
And can you let me know where I was cut off?
Yes. Hang on just 1 second.
Hi, John. We can still hear you on the audio, but we're having trouble with the slides on our end. We've got our connection reestablished, so this is the slide. The general challenges is where we lost, or where we lost control of the slides, but we could still hear you.
Okay, thanks. So the 4 points, and then I'll address those briefly with a bit of detail. So if we could go ahead to the next slide, please. Sampling high-flow environments presents a number of challenges, and one of the issues just briefly mentioned, and I'll state it specifically, is choosing a perspective, and that's a Eulerian, as depicted on the lower left, establishing a grid perspective, or a Lagrangian, following the particles or the beasts of interest as in your reference frame. In high-flow environments, especially say in a river or a high tidal flow, typically we use a Eulerian or a grid-based, and that's the one that we used for our sampling. In any high-flow environment, if you're using some sort of remote or even direct sampling devices, you're going to have an interaction just with the water movement with your sampling. So separating turbulence from biology is quite a challenge. Finally, you're going to also get constraints of trying to directly sample, and that's been hinted at prior, and trying to use a net or some sort of pump or scooping device is going to influence how you sample, when you sample, and if you're getting representative samples. And finally, in looking at a particular site, in these high flow environments, we don't find a large historical collection of data just on the community, on the constituents, and the knowledge of how the dynamics work. So there's a series of challenges going to these sites. Next slide, please. For our instruments and survey design, is this a baseline project looking a backy type issue, or are you actually in monitoring either pre or post installation at a particular site? Are you going to be using direct sampling gears such as nets or pumps, or indirect samplers such as remote sensors and acoustics or optics are the two most obvious choices? With nets, what sort of target species are there and the length ranges which you hope to capture? Are you interested in animals that occupy the water column or those that are near or on bottom? We've heard in examples of both today. For remote sensors, there is a range of long to short scale interests, both in detecting for probability of strikes and looking at movements of individuals and dynamics as they come through. Are you going to be collecting temporally or spatially indexed data? Do you have permanent or semi-permanent monitoring stations that look at a single spot over time, or are you going to be conducting surveys over the immediate and general area? Another important issue in thinking about planning surveys is how to allocate your effort, your remote sensing, your verification samples, and then finally that is all summarized in how you actually lay out your samples and your stations and or your transects. Next slide, please. The issue of detecting change is not trivial in any biological monitoring environment, and especially in some of these cases. If we think about potential impacts, we can think about changes to distributions of animals, changes in aggregation patterns, avoidance in their dynamics and movements, and then also as a big concern initially, strike or impingement of animals on the devices themselves. So the challenge there is to detect, to discriminate species or constituents, then to classify these into groups, and potentially identify if indeed there may be listed or endangered species that are in the environment. We've heard a couple of examples. Are you doing a pattern and process study? Are you interested in just the distributions and dynamics of animals and how they may interact with the devices and their environment? Or are you looking at behavioral cues or environmental cues that actually change these patterns? And these are typically successive steps in any monitoring program. And finally, one of the big ones that, again, is a general issue but does apply specifically to these cases is what actually constitutes change? Are you looking at abundances? Are you looking at differences in densities? Are you looking at those changes as a function of space? And if so, at what scale? Or alternately, looking at them in times of change. We've already seen night versus day and tidal flux types of examples. Next slide, please. The big one, which probably the first steps for the Verdant project in the river, is the issue of scaling up. We may have baseline studies where there are no devices. There may be proof of concept studies where there may be one, two, or a few devices. And then finally, when you have commercial production and arrays of devices, when you may get tens or even, I've heard, up to thousands. So the sampling done for baseline or initial proof of concept, is it additive or multiplicative or some other function when you're scaling up for impacts on communities? Next slide, please. So now we can switch to the specific case study that we're going to be looking at. And we were awarded a project through the National Ocean Partnership Program sponsored by the Department of Energy and BOMER to evaluate potential acoustic technologies to monitor aquatic organisms at renewable sites. There were 4 objectives for the study. We were to choose acoustic technologies to actually monitor nekton, and nekton I'll define as animals that are capable of moving independent of fluid motions, so fish down to macrozooplankton and up to marine mammals. We were to collect baseline data on animal distributions and densities through tidal cycles, thinking that there may be indeed a tidal component to the influence of distributions through space and time. To quantify what stationary deployment acoustic data actually represent relative to our more traditional mobile surface-oriented surveys. And finally, to formulate metrics that could be used to actually index biomass distribution, size, and flux, and thereby be used in longer-term monitoring programs. We had a number of partners in this project. They included the Northwest Fisheries Science Center, the University of Washington, and 3 vendors who were responsible for the actual technologies we deployed on the bottom, which you'll see in a minute: Biosonics, Reason, Soundmetrics, and the surface, Simrad. So let's move on to some specifics. We have the next slide, please.
And about 5 minutes, John.
That looks good, thanks. For our survey objectives, which we ran in May and June of this year, so we're just getting the data all straightened out and going through our quality assurance and quality control for it. We were interested in quantifying the species composition, distribution, and abundance of pelagic fish and macroinvertebrates, the nekton. We also had seabird and marine mammal observer, which was conducted during the surface surveys. We wanted to compare these temporally indexed to spatially indexed data sets. We had acoustic packages that we deployed for 1 month on the bottom, and I'll show you those in a minute. And finally, to recommend methods for future monitoring. The picture in the upper right shows one of the autonomous platforms that has the acoustic camera, a DIDSON, mounted on the top, along with acoustic releases and other instrumentation. So I will show vignettes of these as we go through. And the next slide, please. What we ended up with the survey design was in 2 parts. As mentioned, we deployed autonomous acoustic instrument packages. The left-hand diagram shows a bathymetric map overlaid in the area, and that is the bottom of Admiralty Head, so we're near just Admiralty Inlet, as Brian had introduced previously. We had a multi-beam sonar, a split-beam echo sounder, the acoustic camera, a DIDSON, and a series of water current profilers that would allow us to quantify both the long-channel and cross-channel water motions. So these were looking upward. They were taking data for 12 minutes at a frequency of 1 sample per second every other hour over the month-long deployment. And then we conducted surface surveys before, during, and after this 1-month deployment that included split-beam echo sounders and a multi-beam sonar in coordination with mid-water trawling and, as I mentioned previously, seabird and marine mammal surveys. You'll see we had an intense or a higher resolution sampling right near the point, which was centered on that bottom deployment of the packages, a coarser resolution to the north spreading out to get an aerial representation, and then a mirrored sampling set, what I'll call the south grid, which would give us an indication of a different site to see if they were consistent and to give us a sense of the flux, tidal flux back and forth. Next slide, please. I won't go into many data specifics, but kind of give you an example of the types of data we now have at our disposal. In the upper left, you have a bathymetric representation of the depth distribution in our north grid and the surface pattern over top. The middle picture shows the Biosonics echo sounder data looking up from the bottom from the package toward the surface. We have some interference from some multiple returns from the surface as the sound bounces up and down, and we can to filter that out. In the lower right-hand corner then we have a coincident package from the data echogram from the DIDSON, and you can see in both the middle and lower images kind of a plume event that's coming up off the bottom during that 12-minute where we're getting some probably silt moving up into, and from the echo sounder you got to kind of know where to look, but there's some avoidance going on of that plume, as you can see near the lower right-hand or lower left portion of that slide. The picture there is again the DIDSON. So we had the DIDSON, the Biosonics echo sounder, and the Reason multibeam all looking up in those packages on the bottom. Next slide, please. From the surface, we were trying to characterize the distributions that we saw over time. Up in the upper left-hand corner, we had what was very common, what we affectionately became calling the blue fuzz cloud, and there was largely invertebrates through the water column. Below that, we had individual fish as midwater targets. On the right-hand side, we had larger fish that were typically associated with the bottom, and also aggregations that were found near surface in the bottom. And in the middle, we also had a fair amount of turbulence going on in this region, a high flow area, and you probably can't read it on your screen. And if we get the next slide, the comment there written on the upper middle is, wow, that is some serious rip, and there's a photograph just to show you the dynamic turbulence that we could see expressed right at the surface, and you can see that it's going down to the bottom 50 meters below the surface. Next slide, please. So initially, what did we learn from this exercise? First, that autonomous equipment deployments carry risks. In one case, we really had no data. We had limited data just from the interference that we learned. You could have poor data quality. And often they're non-traditional deployments. These autonomous packages, to Brian's credit, they've developed a system to deploy these platforms and recover them, and that made our work much easier. The autonomous deployments are typically constrained by power. We were all battery driven for these instrument packages. Data storage is not really a constraint anymore thanks to advances in hard drives and even flash storage. The direct sampling is truly a challenge. We were limited with our midwater trawl, which is a small herring trawl, to plus or minus 1 knot of current because of the drag. Adding more boat power really wouldn't add our ability to sample. Ultimately, you need to reduce drag for these nets, and there are new knotless designs or different materials such as spectra that will reduce drags of nets and enable sampling in higher flow environments. And finally, what constitutes a sample and determining change are things that we adapted as we went through our sampling. So finally, on the next slide, we had a series of challenges. Some we believe we met, including that we did choose appropriate acoustic instruments to look at the different technological classes available to us, and that the field sampling design did provide us with appropriate baseline and comparative data streams, both in space, in time, stationary and mobile samples. What are we up to now? Well, we've got our remaining challenges of comparing our stationary to mobile acoustic data streams, and finally formulating these metrics to monitoring these sites as being representative of either site-specific or general sites. And that's it. Thanks very much.
Great. Thank you, John. We actually don't have a lot of questions right now. You must have done such a great job being clear that we don't have a ton of questions. But I will ask one question, and then if the audience has additional questions, please submit them, and we'll either get to them in writing later or in the oral phase here. My question is just referencing back to Marianne's talk, which talked about micro, meso, and macro scales. It sounds like the technologies you're testing here have applications at multiple scales, but what would you say the scale you were focusing on for this project was?
Well, part of it was to address the scaling up issue, and traditionally the acoustic camera has been looked at for monitoring individual devices or getting towards species identification. The multi-beam sonar has a very wide volume, so you are looking at you're potentially looking at areas within the array or as things approach the array, and we look to the split beam echo sounders for long-range detection. Another point that's not addressed is that in combination, these technologies may indeed be able to aid in the tracking of potential threats to arrays and or devices where you have long-range detection, shorter-range classification or warning systems, and ultimately identification as these individual or groups approach the devices.
Perfect. I think that's a great lead-in to our next talk, and if additional questions come in, we'll get them to you in writing, John.
Okay, thanks very much.
Thank you. And so our next presentation, once Anna gets it loaded up, will be from Tom Carlson, who's a senior research scientist at Pacific Northwest National Laboratory. And Tom will be talking about passive acoustic-based compliance monitoring for tidal turbines, again, focusing on this Admiralty Inlet site. So Tom, when you are ready and when your presentation is up, please go ahead.
Okay, looks like I'm good to go. The title has already been given by Simon. So the next slide. You've already heard quite a little bit about the about this particular site that Snowput is planning to deploy tidal turbines at. And so I won't go through all of that again, except to say in this case, the case I'm presenting on, we are looking at marine mammals rather than fish. The role of PNNL in all of this is environmental assessment, acoustics, and peer review of science. This project that I'm going to present is not funded by Snowput and is independent of the effort that they're making to secure their license. Next slide. The problem, and you've heard this several times already, and this plays out, the micro-macro scale of considering impacts. But in the short term, the problem we're addressing has to do with compliance monitoring for tidal turbines, and the challenge is that the regulators want assurance that endangered species of killer whales will not be taken by these turbines, where the concern is similar to that for other species that you've heard about, and that's strike and/or collision with these devices. And a lot of the concern is based on the uncertainty about how these animals are going to respond to the devices. And so a second part of the problem is to deploy a compliance monitoring capability that will allow you to obtain information that hopefully would help reduce this uncertainty. Long term, of course, same issue, how do you scale up to mini turbines and implement a compliance monitoring capability that appropriately addresses the risks that actually occur at those scales. Next slide. The approach that we're taking for the marine mammals that we have an interest in, which are killer whales, is continuous passive acoustic monitoring, where we want to implement detection, classification, and localization capability for vocalizing whales that occur within 200 meters of the tidal turbines. We want to be able to use commercially available off-the-shelf components and integrate them into a passive acoustic system, where our additions will be in the form of algorithms and real-time processing software to perform these three tasks. And then finally, we want to validate the performance of the system and to package what we put together so that it can be competitively procured by utilities if they choose to do so. Next slide. These are the critters that we're monitoring for. They're quite large marine mammals, as you can see. The thing that makes them viable candidates for passive acoustic detection is that they're busy making noise most of the time. They echolocate to find their prey, which in the case of these particular whales, they've specialized on adult Chinook salmon. And they're also quite social. They call a lot to one another to stay in contact. Next slide. The passive array configuration that we've designed uses two what are called star arrays. As you can see in the picture to the left, the arm links on this array about 2 meters. The hydrophones would be located in the holders on the risers that you see at the ends of the array, and then one there in the middle at the center, the origin. Each of the hydrophones would be separated by 120 degrees if you look at it as an angular separation. We'd have 2 of these arrays that each be separated by 20 meters. The arrays would be treated as independent systems, but would be synced to a common clock. And from each of these arrays, a bearing to the sound source or the calling marine mammal will be determined, and then the location of the marine mammal would be found by looking at the cross bearing, or where these two bearings cross. Next slide. The detection approach, this really is detection classification. Those two processes occur in stages. But we use an energy detector to identify candidate signals. Then we then capture those signals and then work on them using a classifier. The first stage of the detection process reduces the amount of data that we have to store, and then process in the second stage, of course, reduces the false alarm rate. Next slide, please. The energy detector, this is the flow of data through the detector. A call comes in or a signal comes in. It's filtered so that we're only looking at a frequency band of interest. And then we implement the detector by summing energy, which essentially is scoring the signal and then summing it. And then when the energy increases, in other words, if the signal has a duration, it's not just a single impulse, by then after a period of increases in energy, why then that part of the signal is written to storage and kept for further classification work. Next slide. This is an example of how this detection algorithm works, and you can see in this particular case the top segment would be the time domain signal as we think of it, and then the bottom would be the output of the detector. And you can see that the areas in green are well calls, and you can see that the detector did successfully detect all of these calls, but it also isolated 5 other areas that were not well calls and wrote those to storage as well. So those would be what we would consider to be false positives and would want to classify out of our detection sequence. Next slide, please. The spectral classifier works as shown here. The audio signal that we've saved comes in. We then do what's called a short-term Fourier transform on it to turn it into a spectrogram. That spectrogram is then processed so that we can deal with it as an image. And the process for doing that involves making sure that none of the frequency components that may be important in terms of distinguishing it as a whale call are weighted less than others, and that's what the pre-whitening filter does. That signal then comes in. We compare it with similar images that we have that you can think of them as templates. And if our binary image fits within a template given some statistical parameters, why then we classify it as a whale call. Next slide, please.
About five minutes, Tom, and audience, if you have
here's an example of what this would look like, the spectrogram coming from the short-term Fourier transfer, and then the filtering on it to get rid of some of the noise, and then it would be pre-whitened to give us the binary image. So this would be the call image that we would then process and either accept or reject as a detected call. Next slide, please. The performance model that we're evaluating against has to consider a sequence of probabilities that have to do with the behavior of the animal and the vocalization that accompanies that behavior. I won't work at this a while, but just to let you know that the factors having to do with detecting these animals, does depend upon their vocalizing, in other words, what they're actually doing at a point in time, and that their vocalizations are linked to their behaviors, where vocalization is more common during some behaviors than others. Next slide, please. We put together some data sets, actually some fairly large data sets that contain whale calls that were annotated so that we knew what we were looking at. We also had have a large set of background files, and then we have some of the common noise files, sound files for some of the common noise sources like boats. And we've gone through and run our detector and classifier on these signals to characterize, or to, I guess, set our expectations for the performance of this system in the field on a
Tom, are you still there? Sounds like, Anna, we may have lost Tom.
Still too high to be acceptable.
So, Anna, are you working on getting Tom unmuted?
Anybody there?
Yeah, Tom, this is Simon. You seem to have disappeared for a second. Are you back?
Pardon?
I think it sounds like you're back up.
Yeah, I think so.
Yeah. Please go ahead.
Okay. Well, that's good. Well, I got through the evaluation slide, and I'm ready for the next slide.
Hopefully it moves Anna here. Anna, can you change the next slide?
Okay, here we go. I want to talk about the localization now, which is the last part of the sequence, detection, classification, localization being the sequence. The way this works is that we have all 4 channels of the array coming into an amplifier. Then it goes through the detector. Binary waveform is saved to storage, and then we use a least squared solver or maximum likelihood to get a bearing to the array, and then we can compute the intersection of the 2 bearings to give us a range. We can process this data quickly enough to get bearing and range estimates in real time, and we're currently working on a 3D solver that we can implement in real time as well to get the 3D position of the calling animal as we continue on in developing the system. Next slide, please. Anybody there?
Is anybody on the line? Tom, are you still there?
Yeah, I'm still here.
Okay, well, I'm not sure what just happened. Hopefully people are still hanging on. I think Anna just had a hiccup. She has no more audio, and she's controlling her slide progression. So let me just send her a quick chat and see if we can get you. So you can see Anna has lost all audio. I'm going to see if I get her to change your slides, Tom.
Right. Okay.
Everything was going just so well, too. Sorry about that.
Mitigation loss at different frequencies is a function of range. These are plots of spherical spreading 20 log R plus absorption. And what you see is as you propagate out, the higher the frequency, the more rapidly it falls off. You kind of go off a cliff of absorption as you go higher in frequency. In sonar design, you tend to want to go as high a frequency as you can to increase your resolution, but also decrease the size of your sonar head. However, the higher you go in frequency, the shorter your range. If you, one click on the slide, please. If you do the design problem, usually you have, if you could click once on the slide. There it is. In the design problem, what you usually do is you usually look for that point where the absorption losses are roughly about 5 or 10 dB more than just spherical spreading or non-absorption losses. And that's kind of your design points for your sonar in a coarse fashion. So you can see it, you know, the left end of 400 kilohertz sonar, you might get out to maybe about 80 meters of range, or at the other end on a 50 kilohertz sonar, you might get out to 80 or 1,000, 800 or 1,000 meter range. Next slide. In the next slide, you have different categories of sonars that we've all been kind of talking about. You have imaging sonars at the top that you can really see an individual fish. The next, you might have fish finding sonars where you see groups of fish as you step down in frequency. And what I'm sort of working on in our project is lower frequency systems where you actually detect at longer range, and on the left side of that is the high-frequency marine mammal sonar system. On the right side is actually a system by Sonardyne for detecting and tracking terrorist divers. Next slide.
Bear with us 1 second.
The application that we've been working on with Scientific Solutions is the one that Gail also looked at, is the Tidal turbine being deployed by the Ocean Renewable Power Company. This unit is the first generation unit that should be deployed next fall, next spring sometime. Next. And the planned sort of monitoring for the system is on the left side. There's going to be, as Gail pointed out, some short-range imaging sonars to actually see and image what's going through the turbine. And then we're also working on the right side of it, which is trying to do longer-term monitoring that integrates with the short-term monitoring. Monitoring, I'm sorry. Go ahead. So the active acoustic monitoring system that we're looking at is the longer range system. Next slide. So swimmer detection systems is the basis for the active acoustic monitoring system. It turns out that, you know, an effective active acoustic monitoring system for offshore renewable energy basically has the same requirements as the signals detection sonars, that have been much more fully developed over the last 10 years or so, since 9/11. They contain automatic detection, tracking, and localization of low target strength objects in a shallow water environment. A lot of them are fairly well developed but very expensive, and classification is still an issue. SSI has been working on a system we call Swimmer Detection Sonar Network, SDSN, and we're using this as the basis for our system for AIM. In the next slide, please.
Hold on 1 second. If any of you listening have your phones or computers unmuted, besides Peter and myself and Anna, please mute them. That may be part of the problem.
Yeah, this is Peter Stein. I actually heard crackling noise, so I think you might be right.
Yeah, and I keep just getting, my phone just keeps getting cut off. I'm not sure if it's a sort of a signal thing or what.
Yeah, I hear a crackling noise.
Okay. Anna, if you're on, please hit the next slide. And Anna, just to confirm, are you with us on your cell phone now?
Hi, everyone. I am on my cell phone now. I apologize for the confusion. So I'm gonna go on mute, and I can communicate through my cell phone now.
Okay, so I will not be texting you. Next slide, please. Just go ahead and hit them when you're ready. Thanks, Anna.
Okay, as I said, the beauty of what we're doing in this swimmer detection sonar network is we're taking a fairly advanced system that has a tremendous amount of development dollars, truthfully, and software and hardware behind it, and porting it over to the AIM application, the monitoring application for the hydrokinetic. The SDSN system is a fixed beam sonar system. On the left is an early version of the system, a current version of the system, I should actually say. We have an advanced node that we developed, but it has 12 beams that search out. Each of those beams points in a different horizontal direction. As you can see, there's a bunch of software and networking, software architecture for the system and signal processing that goes along with it that we're able to leverage for this problem. Next slide. This is a typical output of the system showing in the long track the system tracking a diver. And actually, in this particular run, we tracked something that was following the diver, probably, in this case, a large stingray. There were several sighted in the area. Next. And this is at the distances of 4. As you can see, this is at ranges of 400 or 600 yards. Kind of our major uncertainties going into the system, yep, that's fine, was will the system work in a high current environment, and would it work specifically off of Eastport, Maine? Next slide. So we actually did a trial using the same prototype beta unit that Gail worked with her fish studies, and we deployed one of the sonar nodes on the side of the ORPC barge and tidal turbine. Looking forward, next slide. This shows pictures of the sonar node being mounted onto the tidal turbine frame. Next slide. And we dragged around some test targets. On the left is a test target that we used that simulates a mid-sized whale, and on the right, the person there is holding up a small target sphere that is actually probably simulates something like a small Adonisy, like a seal or a porpoise. And the next slide. This is 6 of the sonar beams, and this is basically return strength as a function of time and mapped into range. So this goes from 0 out to 1,000 meters. And if we're going to click this, and it's going to play a movie, and the system's pinging at a rate of 1 every second. So as this updates, it's a 1 per second evolution. So you're going to see about a 10-minute run go pretty fast. And on the third plot down, you see the target very clearly coming in and moving along to the left and in. And I think we can click that once more and play it again. And if you'll see the target moving along right there, it's actually skipping a few beats, but the target is very clear coming in and moving towards you. You also tend to see a lot of other stuff moving down on you, and it's either schools of fish or debris, so forth, or clumps of seaweed coming in. So you actually detect a lot of stuff, and I think the biggest problem we'll have is being able to discriminate what's a threat to the system or a threat to a marine mammal or a big log that might damage a system versus other stuff in the water column. Next slide. And this is the results of a track of actually the smaller target sphere coming in from 400 meters. So you can see we can quite effectively track quite small targets coming into the device. And this was a very limited experiment, and we expect to do a lot more in the near future when we deploy a system along with the turbine next spring. Next slide. This is the new node that we've developed for the system, and the one on the right is the actual image of the one that we'll be doing. And this is essentially how it will be deployed. There'll be a rosette of these nodes deployed, and actually it will be co-located with the high-frequency sonar that Gail's going to be deploying. So the hope is that we'll be able to see things coming in on sort of a large scale, and then be able to identify them with the high-frequency sonar. That's the end of this first part, and if we go to the next slide, we'll talk quickly about the second part. Active acoustic systems available for monitoring. Generally, most of the systems that have been talked about are high-frequency imaging systems. The one operational system that I know for longer range detection of marine mammals is a system that's on the Navy CERTAS LFA platforms called the HFN3, high-frequency marine mammal monitoring sonars. The AIM systems are under development, and I believe that sort of integration of the systems will lead to the biggest advancements, integrating the longer range and the shorter range systems to understand what's coming down and then what's actually going through the devices. And I think that probably the biggest issue with these AIM systems is the issues related to marine mammal harassment that need to be addressed. You know, are these going to be 24/7 operations? In which case, how are they going to affect marine mammals in the area? Next. The other thing that we've done with ORPC that I think would be of interest to this group is making radiated noise measurements in high currents. It's just a very difficult problem to make accurate noise measurements when you're talking about 5 and 6 knots of currents or even greater. Next slide.
And Peter, this is Simon. If you can wrap it up in about a minute or two, that'd be great.
Okay. Let me just sort of skip ahead. Just click a few times, and what we do, and I'll just talk for a little bit as we go through the time. There are all sorts of problems with flow noise over hydrophones, and what we found is that the best technique for making the noise measurements is to just keep skipping down the slides, Anna. The best way to make these measurements, because of the various issues with how you can deploy things, is to deploy a hydrophone off of a drifting buoy and then let it drift with the current and make the measurements. And we were successfully able to do that with the ORPC Tidal turbine. If you just skip ahead, Anna, to the picture of the drifting noise measurement buoy, maybe. You get cable strum, vibrations of cables if you put things out, noise of flow over them. We did a temporary deployment where we actually did it off of a drifting boat and got some success with that. But then we found that it was better to design to do it off of a spar buoy that had kind of minimal motion in the vertical. We keep going. This is some initial noise measurements. This is actually a soundtrack. And this is a drifting noise measurement that we developed. That was a picture of it. And this is the data results we got from tests. You see on the top left there the picture of the noise measurement buoy drifting along. And then these are actually radiated noise measurements in different currents. And then the bottom right is actually shows you sort of the increase of the noise in the blue over the background noise from the currents. It turns out that the ORPC turbine is actually quite quiet. Really no reason for any marine mammal incidental harassment authorizations. But we were also successful in measuring sort of noise as a function of current with this device. And it does seem like the way to sort of at least do initial monitoring. If you go to the next slide, this is the final slide, I believe. You know, high current, what the conclusion of this talk was is that high current noise measurements can be made from a drifting spar buoy. However, it's kind of labor intensive, so I don't think it's feasible for continuous long-term monitoring. Certainly the ORPC turbine is very quiet. The plan for the ORPC tidal generator is actually to install accelerometers on the unit, and we'll make some initial measurements where we correlate the signals from these accelerometers with the radiated noise, and it's the accelerometers that will provide long-term monitoring to determine if the radiated noise levels have increased, but also for failure detection. And that's the end of my slides.
Great. Thanks, Peter. And again, very sorry for the technical difficulties here. I think given that we're over time, we may move past questions. And I'd encourage folks to get in touch with our speakers. I think your contact information is on your presentations. And as I mentioned, presentations will be hosted on the TIDSON website. Anna, I think you had a couple more slides you wanted me to run through, just to conclude. And thank you for the stalwart 100 people who are still on the line here throughout the technical difficulties. Just wanted to call a couple of additional projects to your attention in this theme of monitoring and for monitoring technologies and strategies. A couple listed here on this slide that were funded under the National Ocean Partnership Program broad agency announcement last year as a partnership between DOE, MRE, DOE, and NOAA. First one is a project led by Pacific Energy Ventures to develop protocols for baseline studies and monitoring for ocean renewable energy. And the second one is a project run out of the University of Rhode Island around developing environmental protocols and modeling tools to support ocean renewable energy and stewardship. And both of these projects are kind of umbrellas, if you will, to start parsing through some of the information you heard today to develop an understanding of how you would select appropriate technologies and appropriate studies for monitoring plans in collaboration with industry and agencies and others. Also, just a note that there's a link here to the Annex 4 data form. If any of you listening in the audience have other technologies or other studies or other data sets that you think would be important for DOE and others to consider, a great place to submit those technologies or studies is to the Annex 4 database, which is an international database in our Ocean Energy System Implementing Agreement number 4, and there, you can see a link there. And also, just feel free to get a hold of Anna Coffey with any other suggestions on projects or other monitoring studies that might be worth us knowing about. So next slide, Anna. As I mentioned, presentations and a recording of this, should you choose to watch it again, are housed at the TIDSON site. You can see the link there. We're also in a period now of considering what the future of the webinar series will be. We've done 3 this year. We do have other topics that we've identified as other potential good environmental webinar topics for next year. And we're in the process of evaluating the effectiveness of this tool and how useful it was to you, the audience. Maybe not the best time to send you a survey after the technical difficulties, but I did want to say that Anna will be sending an email to all of you on the line today with a link to a SurveyMonkey survey, which is just a really quick 10-question survey, which will allow you to give us your thoughts on how you thought this was useful or not, and also suggest potential future topics should there be interest in future webinars. And also, as always, if you just have any other broad general questions, please feel free to get a hold of Anna at anna.coffey@ee.doe.gov. So is that it, Anna? If that's it, thank you all again for hanging on, and this concludes the 3rd webinar. Thank you very much.